I'm R. Prabha, Assistant Professor in the Department of ACE, SNS College of Technology. In this video, we are going to see the topic antenna arrays for the course Transmission Lines and Antennas. First, we see about antenna array. It is a system of similar antennas oriented similarly to get greater directivity in a desired direction, and it may also be defined as a radiating system consisting of several spaced and properly phased radiators. So the total field produced by an antenna array system is the vector sum of the fields produced by the individual antennas of the array system. An antenna array is said to be linear if the individual antennas of the array are equally spaced along a straight line. The individual antennas of an antenna array is also termed as elements. Thus, a linear array is a system of equally spaced elements. And there are various forms of antennas arrays based on the arrangement and also the current, amplitude and phase. So the first case we see the broadside array, where the antennas are equally spaced along a straight line, so we can call it as a linear array, and it is all the antenna elements in this broadside array are fed with current of equal amplitude and equal phase. Here for this broadside array, the maximum radiation is in the plane perpendicular to the array axis. And in contrast to the broadside array, we see we have another type of arrays, an end-fire array. And in the end-fire array, all the antenna elements are fed with current of equal magnitude but opposite phase. And here the maximum radiation is in the direction of array axis. And this is also linear array because all the elements are kept equal space in array axis. And the radiation pattern of broadside array is 8 shape, and where the maximum radiation is in broadside, that is the plane perpendicular to the array axis. And in the end-fire array, the maximum radiation is along the array axis, and in the perpendicular direction there are minimum radiation or zero radiation. So the third type of array we see is the collinear array. So in a collinear array, the antennas are arranged coaxially, that is all the antennas share the same axis and it is stacked one over the other, and the antennas are mounted end to end in a single line. The individual elements are fed with equal in-phase currents as in the case of broadside array. So the collinear array is similar to broadside array except the difference in arrangement of the antenna. And the collinear array is a broadside radiator which the direction of maximum radiation is perpendicular to the line of the antenna or array axis of the antenna. So its radiation pattern is also similar to the broadside array, the 8 shape. And now we are going to see, for analysis purpose, the simplest case of antenna array is 2-element array. So here the array of 2 point sources with equal amplitude and equal phase are kept along an array axis where theta equal to 0. So this is a broadside type of array because the current is in phase and equal amplitude. And here the field pattern of 2 isotropic sources of equal amplitude and opposite phase also we are going to discuss. And the third case we are going to see is array of point sources with unequal amplitude and any phase. So in the array of 2 point sources with equal amplitude and phase, in the diagram we have 2 antennas kept mutual in equal space with respect to the center point, and the total distance between the 2 antennas is taken as d. So it is both are equally spaced from the center, so we can say that from the center point to antenna 1 is at a distance d by 2, and from the center point to antenna 2 is at the distance d by 2. And if we calculate the path difference between the antenna, because here in the diagram the radiation from antenna 2 is arrived at a distant point P very earlier than the antenna 1 because of the path difference between the antenna 1 and 2. So now we are going to check the path difference. So here the path difference is 1 dash 2 dash meters. It is cos theta. If we take cos theta formula for this triangle, it is x by d by 2. So here so this cos theta is calculated as x by d by 2, and x is d by 2 cos theta. So the path difference, half of the path difference is d by 2 cos theta. Again we have the another half, it is again d by 2 cos theta. It is totally added. We get d cos theta meters is the path difference between the antenna 1 and 2. Now we convert the path difference from meters into wavelengths. So it is divided by lambda. So now the path difference in wavelength is d by lambda. And after getting path difference, calculating the phase angle difference, psi is 2 pi into path difference. So 2 pi into d cos theta by lambda, and we can also say 2 pi by lambda is beta. So the phase angle difference is beta d cos theta. So now the total electric field calculation, it is it is the sum of field radiated by the individual antennas. So the first antenna radiation is E1 e power minus j psi, and another antenna it is E2 e power j psi. Now we are taking both the antennas are equally having equal fields. So E1 E2 is taken as E0. So total field E is equal to E0. Within bracket we have e power j psi by 2 plus e power minus j psi by 2, and substituting cos psi by 2 formula, we have the total field finally E is equal to 2 E0 cos beta d cos theta by 2. And similarly, array of point sources with equal amplitude and opposite phase, we have instead of beta d cos theta, we have beta sine of beta E is equal to 2j E0 sine of beta d cos theta divided by 2. So here sine is a formula because the two fields are opposite. So we can write E1 equal to E2 is equal to E0 because both are equal amplitude, but since first antenna is lagging in phase with respect to the second antenna, it is kept in minus. So E is equal to minus E0 e power minus j psi by 2 plus E0 e power plus j psi by 2. So e power j psi by 2 minus e power minus j psi by 2, we have the sine formula. So the final field is equal to 2j E0 sine beta d cos theta by 2. So here there are radiation pattern, it is in the direction of array axis. So now the assessment for long distance communication, which of the properties mainly necessary for the antenna is the high directivity, because if the antenna is having the high directivity, we get sharper radiation, and it is better for distance communication. And the second question, which of the following is false about the single antenna for long distance communication? So the options are given. Here the answer is high directivity, no side lobes, because if the side lobe is so this is false because a single antenna for a long distance communication. Thank you.